So, similarly, we will continue equation of motion in the spherical coordinate system as we have learned for the Cartesian coordinate system. So, here are the three equations, that is r equation of motion, theta equation of motion and z equation of motion. So, here you can note down the equation. The r equation of motion is rho dou Vr upon dou t plus Vr into dou Vr upon dou r plus V theta upon r, dou Vr upon dou theta plus V phi upon r sin theta into dou Vr upon dou phi minus V theta square plus V phi square upon r bracket close equals to minus dou p upon dou r minus whole bracket 1 by r square dou upon dou r square tau rr plus 1 upon r sin theta dou upon dou theta into tau dou upon dou theta of tau theta r sin theta plus 1 upon r sin theta of dou of tau phi r upon dou phi minus dou theta theta plus dou phi phi upon r bracket close plus rho g r. As I have stated you, the r equation of motion you can note down, that is given on our screen, the r equation of motion, theta equation of motion and z equation of motion. So let's continue this.
So let us see the Navier-Stokes equation. What is it and how does it work? The Navier-Stokes equation describes how fluids, liquids and gases move. They are essentially a mathematical formulation of Newton's second law for a fluid element. Force is equals to mass into acceleration applied to a continuum of fluid. How does this work? What is the governing principle behind Navier-Stokes? So these equations, these equations come from three fundamental conservation laws: conservation of mass, conservation of momentum and conservation of energy, which is not always solved together with momentum equations.
In most of the fluid dynamics problem, including transport phenomena, we use the continuity equation where we ensure that mass is conserved, and second equation is Navier-Stokes equation where we ensure that momentum is conserved.
Now what is the general form of Navier-Stokes equation? So for an incompressible Newtonian fluid, the Navier-Stokes equation in vector form is rho del V vector divided by delta t plus V vector dot delta V vector is equals to minus del P plus mu del square V vector plus force vector F vector. Now here rho is equals to density of the fluid, V vector is equals to velocity vector field, T is equals to time, delta P is equals to pressure gradient, mu is equals to dynamic viscosity, F is equals to body forces such as gravity and centrifugal forces, whereas delta square V vector is equals to viscous term, that is Laplacian of velocity.
As these equations include lots of del operator and lots of differential equation, you can refer other videos to learn about how to solve differential equation, differentiation, integration, differential equation and learn about del operator. So let's continue our explanation.
So now we'll go term by term. Inertial terms, that is left hand side.
Rho into dou V upon dou t plus V into del dot V, where dou V upon dou t is the acceleration, that is velocity of change with respect to time, and V dot del V is a change in velocity due to position in the flow field. Together we describe acceleration of a fluid particle.
Now the pressure gradient term, it represents the force due to pressure differences in the fluid. Fluid here naturally flows from high pressure to low pressure. Viscous term.
So let's discuss the viscous term in that equation, that is mu into del square V, comes from the Newton's law of viscosity, which is shear stress is proportional to rate of strength. The Laplacian term del square V captures the spreading out of momentum due to viscosity. Acts like diffusion of momentum. So let's continue.
So next up is body forces. They represent external forces like gravity, which further goes into rotating system. This could include centrifugal and Coriolis forces, which is equal to F vector, that is viscous terms, is equals to rho G vector. Next is continuity equation, mass conservation. For incompressible fluids, delta dot V vector is equals to 0. This means the divergence of velocity is 0.
That is, no net flow in or out of the point which is consistent with the mass conservation.
Coordinate system forms. This is another form of Navier-Stokes equation, which includes, and it also can be written in different coordinate system based on the problem symmetry. Cartesian, in Cartesian form xyz. In cylindrical it includes r, theta and z. In spherical form it is r, theta and rho.
And we have given you the detailed explanation of Navier-Stokes equation in the Cartesian and spherical coordinate system. So you can note down that and learn from that.
So there are some special cases as well, which includes flow type, which have steady flow, irrotational flow and fully developed flow. And the second special case include simplifications, that is, it becomes Euler's equation, del by delta t is equals to 0. It uses velocity potential and the velocity profile becomes independent of direction of flow.
In case of fully developed flow, the velocity profile becomes independent of direction of flow. So we will discuss now the challenges in solving the Navier-Stokes equation.
The equations are non-linear due to convective terms v vector dot del v vector. So it becomes a little bit challenging for the question to solve from Navier-Stokes equation, because there is no general analytical solution in 3D for all situations. And the famous Millennium
Prize problem asks for the proof of existence and smoothness of solution in the 3D case of that Navier-Stokes equation to solve that particular problems.
At last, we just hop on to quickly some applications of Navier-Stokes equation that includes
Aerodynamics, design of aircraft wings, weather forecasting, simulation of atmospheric flow, chemical reactor. As we are the chemical engineers, we are most excited while discussing the application in chemical engineering. In chemical reactor, we use this equation in the various analysis of mixing and heat transfer analysis. In blood flow, biofluid mechanics in arteries,
and in turbo machinery, it is used in pumps and turbines,
which are mostly used in every industry, whichever it may be, the fertilizer industry, petrochemical industry, petroleum industry, and in all the type of industry related to chemicals.
And not only that, it is also used in oceanography, like it is used to measure the wave motions and currents in the ocean. So how interesting is that?
So let's continue with a quick summary of whatever we have discussed to make you more understanding this session.
So to summarize this, we are going to quickly take all the components of Navier-Stokes and show what they represent. So first up is minus delta P, which includes pressure forces, F vector, that is external body forces, delta dot V vector is equals to 0, which means mass conservation for incompressible fluid.
So we have another terms in our equation, that is dou V upon dou T, which is unsteady acceleration, V vector dot del V, that is convective acceleration, and we have mu into del square velocity vector, that is viscous diffusion. So have a quick look on let's continue this session with our case 1 study, and we will derive our velocity profile and give an in-depth study of derivation for the velocity profile. So